Ladies and gentlemen, and welcome to the October meeting of the Royal Astronomical Society of Canada, Ottawa Centre. As usual, we've lined up a lovely program here for you tonight. We have Dr. Avery here from Hertzberg, and please notice the announcements up here, which will soon be covered by the operators with the white screen. So without further ado, I'll ask our Vice President, President-elect, Rob Dick, to introduce the speaker.
This October, we have a speaker from the Hertzberg Institute of Astrophysics here in Ottawa, and Dr. Lauren Avery. And my first, I don't know if you can say, great experience with Lauren Avery is when he taught the first year astronomy course, which now still exists. And I have the pleasure to have been in the first class, and he had the misfortune of teaching the first class, because stacked in the back corner, actually I think it's the back right-hand corner, was about 7 or 8 people from the Royal Astronomical Society of Canada. I'm sure gave him no quarter when things were not terribly clearly stated, or we wanted more and more and more information. And this went on and on and on throughout the whole course. But he persisted to teach that course till around the mid-80s, when a few years after that, I took over the course, so I'm trying to keep on in the fair tradition, though I won't ask him how well I'm doing. He's been busy throughout that whole time studying interstellar molecules, starting with Comet Kohoutek back early in the 1970s, which is recognized, at least by the public, as being a failed comet, but actually was a rather nice comet, and was followed the year later by even a better one called Comet West, but unfortunately that one wasn't as well publicized. Interstellar molecules are interesting in their own right for study, but what is most intriguing, perhaps, at least to Dr. Avery and I think to a number of us here, is using them as a tool to probe the environment, or to study the environment between the stars. It's remote sensing. Astronomy has always been in remote sensing, the epitome of remote sensing, but I think this is even goes beyond that, because you're trying to, using something that we're using remote sense information to probe even deeper into the nature of interstellar space. So without further ado, I believe is the term used, I'd like to introduce Dr. Lauren Avery for this talk, and we'll invite lots of questions afterwards, I hope.
Thanks, Rod. I'm going to have to stand in front of the desk here in order to access the overhead. I hope that's not a problem for you. A few days ago, I was absent-mindedly watching one of these political polls, and it occurred to me that it would be interesting to ask a question of people in the street, to ask them what goes on between the stars in our galaxy. And my guess is that the typical answer would be something like, there's only empty space there, nothing goes on between the stars, and it doesn't matter anyway. Well, anyone who answered that way would be wrong on all 3 counts, of course. The space between the stars is in fact filled with gas and dust. We call that the interstellar medium. And the interstellar medium makes up something like 30% of the total mass in our galaxy. It's a dynamic, heterogeneous, and in many ways a mysterious place. It is the place where new stars form. And of course, if it weren't for the interstellar medium, there would be no stars. And if there were no stars, there would be no planets. And if there were no planet, there would be no Earth. And we wouldn't be here tonight talking about it. I would like tonight, because we don't have as as much time as we need to discuss the whole subject, to limit myself to really talking about the cold interstellar medium, the cold dense component. This is the part that constitutes by far the greatest mass. And I think if we could start perhaps with the few slides that I have, just to give you an idea, although I'm sure many of you already are familiar with the concept of these dark interstellar clouds. I think it's always a shame one should never, I think, give a talk on astronomy without showing just a few colored slides. When nature gives you such an advantage over the particle physicists and the quantum mechanists, you should take advantage of it. This is a, for the focus button, there it is. This is a wide field view taken in the direction of the galactic center. From side to side, it spans something like 50 degrees of sky. And I just chose it in order to show you the extent of the interstellar medium. Of course, the white, bright part of the picture is made up of unresolved stars in the direction of the galactic center. And the other patchy dark stuff is the cold interstellar medium that we want to focus on tonight. This, to my mind, is the most beautiful astronomy picture that there is. It was taken by David Malin at the Anglo-Australian Telescope, and it shows M42, the great nebula in the sword of Orion. This particular object is about 500 parsecs, 1,500 light years away from us. And from side to side, this view would cover, I suppose, about 5 light years or so. This whole region is, in fact, a huge, dense molecular cloud or interstellar cloud on which star formation has occurred on the near forward side. So we see in the region of these hot young stars, the trapezium in Orion, material that has been heated up by the radiation from these hot stars and is glowing at about 10,000 degrees Kelvin. But all around the outside, and indeed threading through the hot gas, you see these dark, wispy tendrils, which are the cold interstellar medium, out of which, or within which, or among which, these stars have formed. Here we have a much more compact example of the cold, dense molecular cloud component of the interstellar medium. This is Bernard 68, about 600 light years away from us. And that dark object there is probably about 1 light year across. The story is told about the German astronomer Friedrich Struve, who worked through much of the past century, the 19th century, that by accident one night he turned his telescope to one of the regions of the sky that had such a dark cloud in it, and is reported to have remarked in amazement to his night assistant, "Mein Gott, ich glaube, da ist ein Loch im Himmel." Good Lord, I think there's a hole in the sky. And you can see why that impression, why you would have that impression. In fact, what we're looking at here is a relatively dense cloud of gas within which there are tiny grains of dust. The dust grains are sufficiently numerous that they block out the visible light. This cloud is in the foreground, and so it appears silhouetted against the more distant background stars. I've referred to these objects as dense interstellar clouds. That, of course, is a relative term. These are objects which are very cold, these dark clouds. This is one in which star formation is apparently not occurring. Temperature is typically 10 or 20 degrees above absolute zero. And the density in these so-called dense clouds is such that the pressure is lower than the very best vacuums we can make in our terrestrial laboratories. And yet we refer to them as dense interstellar clouds. I think that's all for the slides for now. I'd like to go to the overheads. One of the things that people in this field have learned over the past 2 years is that these dark molecular clouds are really amazingly rich chemistry factories. And when I gave a talk on this matter, this subject, about 5 or 6 years ago, I prepared an overhead which showed how our discovery of the different chemicals or types of molecules that exist in these clouds has changed over the years. So I plotted the number, I've called it the number of known interstellar molecules. What I mean by that is just the number of different astrochemicals, if you like, that have been detected in these clouds as a function of time. And you can see that for 25 years or so, things were pretty quiet, pretty moribund in the field of astrochemistry. There were 3 known interstellar medium molecules discovered around 1939 or 1940, CH, CH+, and CN, which were detected on the basis of visible spectrograms taken looking at stars through the interstellar medium. And these molecules showed up by virtue of having very narrow absorption lines superimposed on the stellar spectrum. In 1963, the first radio detection of an interstellar molecular species was made. This was OH, the hydroxyl radical. A couple of years later, people discovered ammonia and water, and then astronomers sort of twigged to the fact that within these dark so-called molecular clouds, there is in fact a rich variety of different chemical compounds. And as you can see, starting in about 1970, the subject took off. As I say, I prepared this overhead about 5 or 6 or 7 years ago, and I didn't have to call the Psychic Friends Network to predict that in the future it was fairly safe to extrapolate, and I predicted that we would have detected or discovered 100 interstellar molecules or types of chemicals before the end of this century. And I indicated that with the dashed line. Well, how have we done? When I was preparing this talk, I thought it would be useful to update that picture. That's overhead. And you can see that things are pretty well on track. We look to be on course for hitting 100 in the next year or 2. Now, what you actually plot here depends a little bit on how you define an interstellar chemical. I don't need to go into details. Suffice it to say that roughly there are about 100 different types of chemical compounds known to exist in these so-called molecular clouds. The most abundant by far is H2, the diatomic molecule of hydrogen. And all of the other things that I'll just mention briefly shortly, are trace elements. But there's one story I want to tell you before I leave this topic. I said that around 1940 there were only 3 known molecules. One of them was the CN molecule, radical. Canadian astronomers played an important role, and spectroscopists played an important role about this time in helping to identify those 3 known molecules, and in particular, a spectroscopist working at the Dominion Astrophysical Observatory in Victoria named Andy McKellar did some very interesting work on the CN radical. He took the 2 lines which had been observed from CN, who predicted that they should be observed based on the earlier work on CH and CH+. The director of the Mount Wilson Observatory went out and looked, and sure enough, the line showed up where McKellar had predicted them to be. And McKellar was able to take the observed ratio of the two lines, the intensity ratio of those two lines of CN, and use them to calculate the temperature of the CN gas that was absorbing the starlight in the interstellar medium. And he published a paper on that result in March 1941, 2 months before I was born, in which he said, we find for the region of space where the CN absorption takes place, the temperature is 2.3 kelvins. Now that was a profound and is now a very interesting result. At the time, nobody, including Andrew McKellar, knew what he had done. He did remark, well, I should say that what he had done was made the very first detection of the so-called cosmic microwave background radiation. This is the radiation remnant that is left over in the universe today from the primeval fireball that accompanied the Big Bang of creation. With the cooling that has gone on in the 18 or so billion years since the Big Bang, that radiation remnant has cooled to a temperature we know today of 2.73 or so kelvins. But it is still around in the universe. And that is, in fact, what McKellar had measured or detected when he published this result. He had no idea, of course, what he had done. It was too early by 25 years to think about primeval fireballs and radiation remnants. But he did remark somewhat ironically, I underlined it at the bottom of this page, that the validity of the various temperatures discussed above will be greatly clarified as our knowledge of the physical state of the matter in interstellar space improves. In fact, the radiation remnant from the Big Bang, the microwave cosmic background radiation, didn't come knocking at astronomers' doors again for something like 25 years. And when it came back, it still knocked rather lightly at the door. As you may know, the actual recognition of this and discovery of this, or perhaps I should say rediscovery of this radiation remnant, was done in 1965 by two Bell Labs engineers, Arno Penzias and Robert Wilson, working in New Jersey, who were trying to calibrate a very sensitive radio telescope, radio antenna, and they were being plagued by this low-level hiss or noise they were picking up wherever they pointed their antenna. The story of that whole scientific discovery is a fascinating one, and we don't have time to talk about it today. But suffice it to say that what they had in fact detected or redetected was this kind of radio wavelengths, the 2.7 degree radiation remnant, the cosmic background, and for that they won the Nobel Prize. Now, just to give you an idea of what these 100 different chemical compounds are, before we talk a little bit about why they're important, this is a slightly dated overhead. I hope you can see at the back. Is there any way of dimming a little bit the front lights without putting the room in total darkness? You will note, I don't expect you to assimilate all of the fine print here, but just a few points I'd like to make. First of all, you'll notice that there are a number of rather familiar terrestrial molecules detected in these interstellar clouds. Things like ammonia, carbon monoxide, water vapor, and other well-known terrestrial compounds are seen. As I said, by far the most abundant is H2. All of the rest of these things are trace elements, but it turns out they're very important trace elements. Some of us are more familiar than others with some of these chemicals. For example, here are the two alcohols, ethyl alcohol, which is the drinking kind, just above it, methyl alcohol, which is not the drinking kind. There's a story again about the discovery of ethyl alcohol, which is somewhat interesting. You may be aware of the journal, the Astrophysical Journal, which is the professional journal for astronomers, the most important professional journal for North American astronomers. And as befits a professional journal that's over 100 years old, the Astrophysical Journal takes itself rather seriously. You look at it, it has a rather dour, dull gray cover on which there are never any pictures, let alone color pictures. That kind of thing is left for amateur publications like Sky and Telescope, considered quite crass, I think. But in the journal issue of 1975, in which the discovery of ethyl alcohol was announced, there was, for a change, an opportunity for a slight chuckle as you read the paper by Zuckerman and his colleagues. The discovery of this alcohol, ethyl alcohol, was made in the giant molecular cloud Sagittarius B2. And these authors pointed out that if you could, of course it exists in the gas phase, but they said if you could purge the ethyl alcohol from all these other noxious chemicals with which it coexists and condense it down, you would have 10 to the 28 fifths of alcohol at 200 proof. Now, I'm not a drinking man, but I do know that 10 to the 28 fifths is an awful lot of booze. And in fact, it would far exceed the total fermentation efforts of all of mankind since the beginning of time. The story is also told, and again, this may be apocryphal, but at the AAS meeting at which this discovery was announced, there was a representative from a major distillery in the audience, because he had heard that there was to be some interesting new news about ethyl alcohol. He was quite disappointed when he learned that this stuff was actually 30,000 light years away and quite inaccessible. It's also not uncommon to have notes in proof added after journal articles. These are little addenda that are added too late to get into the main article, and so they appear as a note in proof. This article, if you look it up, has a note on proof. And it was quite feasible for them to calculate. After all, proof is simply a measure of the concentration of alcohol compared to water. It's a measure of how strongly you diluted your booze. And because water had been detected already in Sagittarius B2, they could calculate the ratio of abundances and publish what the proof of the alcohol in Sag B2 was. The other thing I want to mention before I leave this overhead is the presence of these carbon chain molecules here. These compounds are quite remarkable in that they consist of long strings of carbons terminated on one end by a nitrogen atom and on the other end by a hydrogen atom. The whole family starts with HC3N, and successively longer chains up to HC11N have been detected. This work was done in the 1970s by a chemist named Harry Kroto from the University of Sussex, working in collaboration with astronomers here in Ottawa at the National Research Council. And the actual discovery of these carbon chains was done with the Algonquin Radio Telescope up near Pembroke. I won't say any more about that now, except, well, let me just say one more thing. At the time, this work was really quite surprising. These were then, and perhaps, depending on whom you talk with, still are the heaviest known interstellar molecules. Certainly, they are the longest linear molecules known in heaven or on Earth, and the longest ones, HC11N, has never been synthesized in a terrestrial laboratory. So this was really quite an astounding event in terms of astrochemistry in the 70s. It surprised a lot of people. And I want to come back to these at the end of my talk. Very quickly, as I mentioned, a fair number of normal terrestrial compounds here, but also a fair number of what we might call extraterrestrial chemicals, very reactive ions and radicals, things that are very difficult or impossible to make under terrestrial conditions, because as soon as they're made, they immediately react with the wall on the walls of the container or with other partner compounds and form other more stable, less reactive compounds. In these interstellar clouds, of course, the densities are so low that these highly reactive compounds don't have that opportunity. In the atmosphere in this room, if we imagine sort of a sugar cube size volume of gas, there are 10 to the 19 air molecules inside that volume, 1 followed by 19 zeros. In a similar size volume of dense, so-called dense molecular cloud, there are 10 to the 4th molecules, mostly H2. Each air atom in this room undergoes a collision with a partner molecule, a different partner, something several billion times per second. You see, they have lots of opportunities to react. In a molecular cloud, the mean time between such collisions is something like 30 days. A molecule in a dense molecular cloud travels a few million kilometers between collisions. In this atmosphere here, they travel about 10 to the minus 5 centimeters between collisions. So you can see why the chemistry can produce quite different kinds of compounds. You might wonder how it is that we can identify for sure the presence of these 100 different, somewhat exotic, in some cases, chemicals. It is because each type of chemical has its own signature spectrum. These molecules have rotational energies, they're rotating end over end, and that energy is quantized. In other words, each molecule cannot have any rotational energy that it wants, but the energy comes only at certain discrete permitted levels. And the distribution of those energy levels is unique for each kind of molecule. So that the spectral lines which are produced from these rotating molecules are characteristic, uniquely so, of each different type of molecule. The wavelength at which those rotational energy lines tend to come out are quite long. They're centimeter wavelengths, millimeter, submillimeter wavelengths, very long compared to optical wavelengths. And it turns out that for that reason, we can see inside these dark molecular clouds and detect the spectral lines given off by these different chemicals. That's one reason why they're very important. The optical astronomer sees up to the front edge of these dark clouds, and that's it. You cannot see at visible wavelengths inside where the stars are forming, where the action is. So these molecules, because of the spectral lines that they emit, give us a window inside these stellar nurseries. Here's a sample. It's hard to tell what's data and what's dirt. Here's a sample spectrum. It's chosen at random. This happens to be at a wavelength range of around 2 millimeters, taken with the JCMT telescope. Again, of M42, the Great Nebula in Orion. You can see that it's chock-a-block full of spectral lines from various different chemicals. Here's another example. This happens to be one of the lines from the carbon monoxide molecule. Notice that it has very broad skirts. Now, astronomers like to plot intensity vertically, and very often instead of frequency, they will plot Doppler shifted velocity across the bottom. What this shows us is that in this particular cloud, there is gas streaming at velocities of up to plus and minus 70 kilometers per second. That's what this axis is, kilometers per second, relative to the rest frequency of the cloud. So this illustrates another reason why these compounds are important, because the Doppler shift, the shape of the spectral lines which they emit, can tell us a great deal about the kinematics, about the internal dynamics of the dark cloud. So we can tell whether the cloud is collapsing, perhaps to form a protostar, whether it's expanding, perhaps because of a bipolar wind from a newly formed star. We can tell whether the whole cloud is rotating. Very valuable dynamical information from the Doppler shapes of these lines. Also, by measuring the relative strengths of different lines, we can do exactly what Andrew McKellar did 50 years ago. We can estimate the temperature inside these clouds, and we can estimate the densities. So these compounds are very important, even though they're trace abundances compared to H2. H2, it turns out, is a mute molecule. It doesn't have a dipole moment. It's a perfectly symmetric molecule. It doesn't emit spectral lines in the radio part of the spectrum. So consequently, we have to trace what's going on in these clouds by looking at these much less abundant compounds. I should mention that in addition to rotating end over end, molecules can also undergo vibration, so that the distance between two atoms can change, sort of like as the weight on a spring will bounce up and down. Or if you have more than two atoms, you can get the molecule actually bending the way a door hinge can bend. These so-called vibrational modes of molecules also produce spectral lines, but the energies associated with them are much higher than the radio wavelength, millimeter wavelength lines we're talking about for rotation. They tend to occur, the vibrational spectra tend to occur at infrared wavelengths. And generally speaking, these clouds are too cold to excite those higher energy emissions. We'll see that there are exceptions to that in regions of star formation, where you get a bright, hot young star heating up the gas around it. That can excite vibrational spectral lines. Now, I've said quite enough about the gas. Let me turn briefly to the dust. It makes up only 1% by mass of the interstellar medium, but it's extremely important because, as we've seen, it provides the shielding that, in fact, allows these gaseous molecules to form. The interstellar medium is a very harsh environment. It's full of ultraviolet radiation that would normally photodissociate these chemicals. The dust acts, as we've seen, to make these clouds opaque to ultraviolet radiation. It exists everywhere, although it is patchy. It's distributed all over the sky. And the cumulative effect of the dust is to diminish the starlight that reaches the Earth. This is an effect that astronomers call extinction or reddening. It just refers to the fact that starlight is blocked as it passes through the interstellar medium, being scattered sideways or absorbed by the dust grains. You can measure what that extinction is, and it turns out to be significant. In fact, if there were no dust in the Milky Way galaxy, you would have no problem standing outside in the, shall we say, the darkest night at midnight and reading a newspaper. On average, there are something like 3 visual magnitudes worth of extinction for every kiloparsec that starlight has to travel through our galaxy. That extinction is not flat with wavelength. You can measure the blockage or the extinction of starlight as a function of wavelength. And here, unfortunately, the author of this paper used terrible units, but I've drawn in what I prefer, angstroms. You can see that the absorption, this is a measure of the absorption increasing upwards plotted against wavelength. Ultraviolet light at this end and infrared light at this end. The shape of this curve tells us right away that the dust grains which are causing this absorption are small, first of all, and also that there is a range of sizes. The reason is that dust particles scatter light most efficiently of wavelength that is comparable to their size. So if we had dust grains of only one particular size, what we would see in this kind of a curve is that for wavelengths smaller than that size, we would be getting total extinction. This spot would be off the scale of the ultraviolet end over here. If you look at a candle behind a boulder, that light is totally blocked. Then as we came to longer wavelengths, if the dust was all at one size, we would eventually reach a wavelength where it became longer than the dust grains, and the wavelength of light would then be able to pass around the dust grains unimpeded, and we get no extinction. So we'd see something like this kind of a function, if a step function, if all the dust were the same size. So what we know from this kind of a plot is that the dust grains themselves, although they're very tiny, they do range in size from about 1/10,000th of a millimeter for the biggest grains that are blocking down here in the infrared, to perhaps 1/100,000th of a millimeter for the grains that are blocking the ultraviolet light. The composition of the dust grains is not well known. Generally, it's thought that they consist of silicate cores or possibly graphite or possibly a mixture. Graphite, of course, is a form of carbon. It's the same kind of carbon that exists in the lead of a lead pencil. I want to talk about this central bump here. This occurs at 2200 angstroms wavelength, and you see it wherever you look, whatever direction you look in the galaxy. Many people traditionally have tried to model and explain this, and it's commonly thought that it comes from graphite grains. Grains of pure carbon in the form of graphite in the interstellar medium. As you all know, carbon comes in two different forms: graphite, grains, lead pencil, and diamond in your engagement rings. At least that's what people have thought up until quite recently. Now, I'm going to not say any more. I could talk more about grains, but I think I'll let that go for now. I want to move on now to two of the more puzzling aspects of the chemicals in the interstellar medium. These two things I want to talk about are the so-called unidentified infrared emission features, or the UIRs, and the DIBs, the diffuse interstellar bands. About 15 years ago, when the field of infrared astronomy began to get sophisticated, it was discovered that there are a series of emission features detected at wavelengths between 3 microns and about 11 or 12 microns in the infrared part of the spectrum. This slide shows such a spectrum from the planetary nebula NGC 7027, and if you imagine connecting the dots in this picture, you can see that there are emission bumps. This is now emission plotted upwards, not absorption as in the previous slide, at 3.3 microns, 6.2, 7.7, 8.6, and 11.3. People were not able to identify what could be causing these, and hence they got the name unidentified infrared features or emission features. I won't go through the arguments about what people thought they might be in the early days. Suffice it to say that in recent years, let's say the last 5 years or so, there's been a growing consensus as to what's causing these things. The cause of these UIRs is thought to be a family of molecules, chemical compounds, that's well known for years to organic chemists, but strangers to astronomers. things called polycyclic aromatic hydrocarbons, or PAHs for short. So we can say that we think, at least many people think, that PAHs are the origin of the UIRs, maybe also the origin of the DIBs. We'll come to that. Anyway, what are PAHs? Let's just take a minute to explain. It's a terrible, terrible name. Let's work backwards. Everybody, I think, has a feeling for what a hydrocarbon is. It's a molecule made up of carbon atoms and hydrogen atoms. Hydrocarbon. The term aromatic simply refers to the fact that in such a hydrocarbon, not all of the chemical bonds that tie together the carbon atoms are occupied by other compounds. An example of such an aromatic hydrocarbon is benzene, famous benzene ring, which is sketched here in the top. You see 6 hydrocarbons in a ring, and attached to those 6 carbons are 6 hydrogen atoms. But notice these double lines between the carbons. Each line represents a bond, and you can see that there are 3 unoccupied carbon bonds that don't have other than carbon atoms on them. This is an example of an aromatic carbon ring. Here we have an aliphatic or fully saturated carbon ring in which all of the available carbon bonds are taken up by hydrogens. We don't want to say anything more about that. The polycyclic term, simply as you know, means multiple rings, multiple cycles of carbon. And here, for example, is naphthalene, which we get by linking 2 benzene rings together, stripping off a couple of hydrogen atoms here. And that is really, naphthalene is the simplest true polycyclic aromatic hydrocarbon. Benzene is sort of a degenerate, pathological single ring. I guess you call it a monocyclic aromatic hydrocarbon. Anyway, as I say, these things are well known to organic chemists. They occur naturally on the Earth in marine fossils, for example. But until recently, they were not well known to astronomers. They happen to be rather nasty things to work with. Many of them are carcinogenic. But once they're made, they tend to be very stable, particularly the larger ones, which is a requirement because they have to exist in the rather harsh environment of the interstellar medium. Well, you can keep adding more and more carbon rings together. You get a whole family of these polycyclic aromatic hydrocarbons. Here, chemists are lazy people. They don't like to draw hydrogens where it's not necessary to draw them. So you can picture that there would be hydrogen atoms attached onto the outsides, the peripheries of these compounds. When this idea was first put forward, starting in 1981, not a great deal was known about the spectra of these PAHs. But because of the great interest in identifying what's causing these unidentified infrared features, more and more work has been done in the laboratory, and more is understood about what wavelengths, what frequencies this family of molecules should emit at. And recently, in fact, just in this month's Astrophysical Journal, with the gray cover and the dull titles on the page, there is a paper by a group in which they calculated theoretically what the spectrum of a family, a whole collection of these PAHs should be. They included in their calculations started with rather larger compounds than I've shown you here, made up of something like 60 or 80 carbons, going up several hundred carbons. And their calculations, I think, are rather convincing. Here is an observation, this time in a region of the Orion cloud that we've talked about before tonight. And you see again the observed rather strong emission features that we're trying to explain here. What these people have done, as I said, is to synthesize with a computer, predict what a collection of these black PA molecules might be expected to produce. And unfortunately, the scale is not quite the same, but if I slide this across, you'll get the picture, I think. Perhaps I'll just put this on by itself. That's the computer model which they've come up with, and it does fit, I think, rather convincingly the observed unidentified infrared features. There, for example, is the 3.3 micron feature. Here is the 6.2 micron feature, and 7.7 and 8.6 micron, and over here at the right, 11.3. These different emission features can be matched up with different kinds of vibrations now, not rotations, but wigglings of the atoms in these PAs. For example, the 3.3 micron feature is thought to be a stretching of the CH bond. We said there are hydrogens tacked on the edges of these molecules. They can stretch in and out, and the characteristic wavelength for that is 3.3 microns. Others of these things, 6.2 and 7.7 micron features, correspond to the carbon-carbon bond stretching, and the long wavelength features at 11 and 12 microns correspond to the hydrogens tacked onto the edge of these, the rings of these PAs, bending. They can either bend back and forth in the plane of the molecule, that produces the 11.3 micron feature, or they can bend up and down like that. I'm sorry, it's the other way. Out of the plane produces 11.3, and in the plane produces the 8.6 micron stuff. So, just to summarize that, I would not say that there's unanimous agreement that we know what's causing these unidentified infrared features that show up associated with the dust around hot young stars. But I think it's looking at least plausible that they are these polycyclic aromatic hydrocarbons. I want, in closing, to come and talk about the diffuse interstellar bands. The first of these was discovered more than 80 years ago in 1911. Generations of astronomers have come and gone without being able to explain what causes them. And if we could go to the next slide, I'll just show you what they look like. These are detected, again, in the optical part of the spectrum, visible wavelengths, when you look at the light which passes from a distant star through the interstellar medium. Here are spectra of 10 or so stars, and forget about the dark features, those are reference spectra. The stellar lines are these bright or light features. And a number of the diffuse interstellar bands are shown here with black numbers. For example, here is the 5780 diffuse interstellar band. There are about 40, or perhaps more now, of these bands identified in the visible part of the spectrum. Since their discovery, as I said 80 years ago, a tremendous amount of observational, experimental, and theoretical effort has gone into trying to find out what causes them. And to date, there has been no success. And this must surely be the most outstanding puzzle of spectroscopy insofar as it relates to astronomy of all time. There have been other puzzles that took a long time to solve, but nothing has gone on for 80 years like this. I'm going to skip over a lot of the details and come up to the present time, or not quite to the present time, to 7 years ago. People have argued about whether these diffuse bands are caused by grains or whether they're caused by large molecules in the gas phase in the interstellar medium. We know if they're molecules producing them, they have to be fairly big. Let's say more than about 20 carbon atoms, because smaller molecules than that are not robust enough to stand up to the ultraviolet photons. Remember, this is optical light, so so that we're not looking at stuff that is protected by the dust grains, by and large. Whatever this stuff is, it has to be rugged and tough because it's subjected to the ultraviolet photons in the interstellar medium. Remember Harry Kroto and his interstellar grains. He was in interstellar chains, the work done in collaboration with astronomers here. Harry was fascinated by the question of how these big carbon chains could form in the interstellar medium. And in 1985, he had occasion to visit the laboratory of Richard Smalley at Rice University, where they had what was called a laser vaporization machine. And this laser vaporization machine was really rather simple in concept. It consisted of a powerful laser that could blast graphite, which remember is one of the elemental forms of carbon, vaporize it in a helium atmosphere, and then pass that resultant gas with the embedded vaporized graphite particles into a chamber where the mass of the resultant particles could be measured with a mass spectrograph. Kroto was very interested in using this instrument because he felt that it mimicked the conditions necessary to form these big carbon chains that had been detected in space. And he wanted to see whether he could learn about how these big chains form and whether he could perhaps make even larger chains. So in collaboration with Smalley's group, he undertook the experiment. The results of that experiment were quite simply sensational. He saw, indeed, the big carbon grains, chains, the HC7N and HC11N, and even bigger chains. But he saw something, or they saw something more than that. What they started with, remember, was graphite. Graphite consists of these sheets, if you like, of carbon rings linked together, extending in all directions, piled one upon the other. That's one reason why graphite is a good lubricant, a dry lubricant, because these sheets of carbon can slide easily back and forth one over the other. This is the stuff they vaporized in their vaporization machine. When they looked at what they were getting out the other end, they were astounded. They, with their mass spectrograph, were able to measure the number of carbon atoms produced in each of the molecules, or in the molecules that were being given off by this device. And initially they saw this kind of a distribution here, where there were peaks of carbon not corresponding to 7 or 11 carbons, but dozens of carbon atoms in each molecule. When they fine-tuned their equipment, increased the helium pressure a bit and the flow tube a bit, what they were able to do was essentially produce pure carbon-60. This spike, for those of you at the back, this big spike corresponds to a molecule made up of 60 carbon atoms. Not 61, there's no hydrogen here, not 59, but 60.000 carbon atoms. A totally unexpected, astounding result. The immediate question they had to ask themselves was, what's happening here? What, are we looking at a chain that's 60 atoms long? What, are we looking at chunks of planar graphite that contain 60 atoms? Why 60 atoms when you start out with great, huge amounts of graphite? They thought about this amongst themselves, and in fact, there's some argument within the group as to who had the first idea of what was going on here. That's, for us, not important. What's important is what they did finally agree was happening here. What they decided the shape of these 60 carbon atom molecules was that of a truncated icosahedron. You all know what that is. Well, you do, but you may not realize it. We've all seen truncated icosahedral structures. If you drive around Ottawa on any summer afternoon, particularly on a weekend or in the fall, you'll see kids playing soccer. And a soccer ball is a very good representation of a truncated icosahedral structure. Soccer balls are made up of generally often black and white patches of leather sewn together, right? And if you picture a soccer ball in your mind, picture the seams sewing the patches of leather together. They come together at vertices. They join together. If you had a soccer ball here and you counted the number of those seam intersections, the number of those vertices, you'd find there are 60 of them. And in fact, what these guys had discovered in 1985 was revolutionary. It was and is the third form of carbon. We mentioned graphite and diamond. Carbon comes in a third form. It looks like that. The other place where this shape is seen and known is in the geodesic domes that Buckminster Fuller, the architect, has designed. And in honor of that work, these chemists called their new molecule, C60, Buckminster Fullerene. And there's a carbon atom in this molecule, each of these vertices. And if you count them, if you go in behind and count them, there would be 60. So this was 1985. This paper produced a revolution in chemistry. Initially, it was a bit hard to do a lot of work with this simply because it was difficult to make the stuff in very big quantities. You had to make it in the gas phase according to the original scheme in the laser vaporization machine. And it was hard to get hold of enough stuff to work with. It was by far the most expensive kind of carbon you could get. I mean, graphite is worth nothing. If you break your pencil, you throw it in the garbage. Your diamond ring traditionally has been quite expensive, for the beginning of time, the most expensive known form of carbon. But during the first 5 years of its known existence, this stuff was by far the most expensive form of carbon. Nowadays, thanks to some work done in 1990 by chemists at the Max Planck Institute and the University of Arizona, you can buy this stuff through the mail. It's relatively cheap, about $2,000 per gram. The revolutionary work that followed the discovery of this that really broke the field open by allowing a significant amount of it to be made was done by Kretschmer and his colleagues. And what they do very quickly is they again have a chamber in which they have helium gas at about a 10th atmosphere pressure, and they simply vaporize graphite. Start with graphite. It's got the right basic cell structure, right? And they let this vaporization occur inside their closed chamber for a period of time. Then they take the lid off, and any of you who have worked with carbon can understand what they would see. What they see is the inside of their chamber coated with soot. They scrape the black soot off, dump it into a test tube filled with benzene, and the carbon-60 dissolves into the benzene, produces a beautiful wine red solution. They let the soot and other debris settle into the bottom of the test tube, or perhaps they filter it, and they're left with the carbon-60, the C60 solution in benzene. They dry the benzene, and the C60 is left behind as a brown residue in their container. And they remark in their paper that a technician working in a day produces about a gram of this stuff using this procedure. And I think the last slide, if we could have it, shows you a picture, electron microscope picture of what crystals of this stuff look like. To give you, this is again taken with an electron microscope. To give you an idea of the scale, one of these crystals here is about 1/100th of a millimeter across. Now these are crystals of C60. They're not molecules of C60. Each of those crystals contains many molecules. The molecules themselves are only 7 angstrom spheres. But you'll notice that it comes in different forms. There are thin platelet crystals, there are rods, and there are even stars. The point is, this is pure Buckminster fullerene. This really initiated an explosion in fullerene chemistry. And it's not an exaggeration, I think, to say that the chemistry of fullerenes is quite simply the hottest scientific activity that there is today. But this is an astronomy talk. Let's come back to astronomy. We left astronomy talking about the divs. We thought we might have explained the UIRs, and we said that for many years people have attributed the 2200 angstrom absorption bump in the general extinction curve to graphite. But none of those things are absolutely certain. And remember, the initial motivation that Proto had to do this work was to try to explain how big carbon molecules could form in space, and he had in his mind explaining the diffuse interstellar band. Well, once Kretschmer had made enough of this stuff that he could determine its spectrum, of course, that was of great interest, and immediately what he did was to take a spectrum and dig out his appropriate issues of Astrophysical Journal and try to match his C60 spectra with the wavelengths of the unidentified infrared features. It didn't work. The black line, now we're back to plotting absorption positively. The black line here is the absorption spectrum of the C60 molecule, and I've superimposed on that the wavelength positions of the unidentified infrared features. They clearly don't match. So I think this is somewhat sideways, backdoor evidence, I suppose, in support still of the PAHs, the PAWs, are still in the running as the carriers of the unidentified infrared features. What about the divs? What about the diffuse interstellar bands? Here from the same paper is a spectrum of C60 in the visible and ultraviolet part of the wavelength range. Forget, these are just two different concentrations of the stuff. Forget about the 0.9 micron concentration. The diffuse interstellar bands, you may remember, are at visible wavelength between about 4,000 and 8,000 angstroms, or 400 to 800 nanometers, this part of the scan. There's no sign of any absorption features there. There is evidence, again, this is absorption plotted vertically, there is evidence of absorption here at around 2,200 angstroms, matching what has been traditionally called the graphite bump in the general extinction curve. But you'll notice there are these cursed other bumps, a great huge one here, a great huge one here at 350 nanometers or 2,500 angstroms that don't show up in the observed interstellar extinction curve. So the short, rather disappointing answer was in 1990, as a result of this work, that C60, Buckminster fullerene, does not match the observed astronomical features. It's not quite the end of the story. Astronomers are resourceful or perhaps desperate, depending on your point of view. And a man named Adrian Webster at the Royal Observatory in Edinburgh and others have suggested that although pure C60 may not suffice for this, that it's possible to do a lot of things, chemically speaking, with carbon-60. And Webster has suggested that, indeed, this is a good, and Proto himself has argued that, indeed, this is a prime candidate to exist in interstellar space. C60 and its derivatives are known to be rugged. They're big enough that they can withstand the direct hit from a UV photon and not get shattered. They tend not to react with, well, I should not say that. The reaction which is most likely to happen to them in space is hydrogenation. There are a lot of carbon atoms situated around this soccer ball molecule. We know that hydrogen is the most abundant element in space, so it's not unreasonable to think that hydrogen could be added on, sort of like hair, onto a cue ball or a billiard ball around the outside of these C60 atoms. And so Webster has predicted, he said, right, pure C60 won't cut the mustard, but I think that C60H sub m, where m is some integer, from 1 to 60, should exist in the interstellar medium, and he presented arguments why, generally speaking, it could produce the diffuse interstellar bands and possibly the 2200 angstrom extinction bump. Well, of course, he's a theoretician, and he could make that prediction with a good deal of, without much fear of being contradicted, because nobody knew really when he made it a couple of years ago what the spectrum of C60H sub m molecules might look like. Since that time, some chemists have actually synthesized C60H2. Here you see it. The two little antennae here at the top are the two H atoms stuck on to the carbon-60 frame. And, of course, you know what they did. They went and measured its spectrum, because everybody knows about the DIBs. Everybody knows that they've been around for 80 years and can't be explained. And everybody, even chemists, with apologies to any who are in the crowd, know that astronomers would give their eye teeth to find out what's producing those diffuse interstellar bands. So Henderson and Cahill measured the spectrum of C60H2. What did they see? The bottom curve here, curve B, is what I showed you previously, the absorption spectrum of pure C60. It's what Kretschmer and his colleagues measured a couple of years before this. Curve A is the corresponding absorption spectrum of C60H2. You see it has the same problems as C60. It's sure enough got a strong absorption around 2200 angstroms. That's good. But it's also got absorption peaks at longer wavelengths that line up with those in the C60, and that's bad, because we don't see those in the real sky. Well, Webster, he's disappointed by this result. He published a paper very recently about it. But he says, don't give up the ship yet, folks, because I noticed that in going from C60 to C60H2, that those two unwanted peaks at around 2600 angstroms and 3400 angstroms, here and here, are weaker and broader in C60H2 than they are in C60. Now, in my original paper, I said C60HM, where M could go from 1 to 60. And so he says, it looks to me quite reasonable to speculate that if we go to C60H5 or C60H10, that these secondary peaks might become so narrow, so broad and weak as to not be detectable in the interstellar extinction curve, leaving just the 2200 angstrom peak, which could account for the observed extinction bump. Well, I think I'd like to sum up. That is really where we have to leave the story. You'll notice the date on this reference is 1993. So you're pretty much up to the current state of the art in trying to determine the astrophysical significance of these C60 molecules. But that's not really the whole story, because the whole discovery of C60 has really turned the whole scientific community upside down. And it has spawned a vast number of multidisciplinary research projects. Indeed, as I came in and sat down at the front of the room here, I noticed the notes left over from the previous chemistry lecture, which had C60 written all over the board and fullerene. This stuff is very much in the eye of the chemists and not just the astronomers. Just last week or a month or so ago, I came across this article in Current Contents, which is a journal which specializes in recording all of the references to published scientific papers. And this journal said, referring to Kratschmer's breakthrough in 1990 of being able to make sort of gram-sized quantities of this stuff, as soon as the chemistry community could obtain enough C60 to explore its properties, fullerene fever spread like wildfire. The study of C60 and other fullerenes is the hottest area of science today. It accounts for 9 of the 23 hottest papers of 1991. Elsewhere in this article, Croto, who was being interviewed by the writer, was asked what all interviewers ask of science. What good is it? And he had to say, look, it's really early days yet. This stuff has only been known for about 7 years. But there are a whole host of potential important applications for C60 and its derivatives. And he just mentioned some of these. I won't spend a great deal of time on this, but it's known that the C60 buckyballs, as they're called, can act very efficiently as catalysts. If you use Buckminster fullerene, for example, to spread a film on top of silicon base, you can manufacture synthetic diamond, which has important commercial activities as a grinding element, 8 orders of magnitude faster than if you don't put the buckyballs down first on the silicon. Because these things are round spheres, it's been postulated that they might make wonderful lubricants. We've been using graphite, which is flat stuff, for many, many years. Going to buckyballs, which are round things, is going to be sort of like analogous to inventing the wheel, perhaps, for lubrication science. If you take, or if the environment is right, you can stretch these balls into long tubes called bucky tubes. It's already known that conventional carbon fiber is some of the strongest, most stiff, rigid material available, and it's quite possible these bucky tubes could be used to make extremely high-strength small fibers. People talk about using them as pharmaceutical magic bullets because you can put stuff inside the carbon cage. It's been demonstrated that metallic atoms can be inserted inside. Actually, I think you don't insert them inside the cage. You put the lanthanum atom there, and you let the cage go around it, and you wind up with sort of a ship in the bottle effect. It's speculated that you might be able to embed certain drugs or perhaps radioactive particles inside the cage and send the Buckminster fullerene molecules to the place in the body where that dose needs to be delivered. If you're just looking for radioactivity, you don't need to open the cage, you can just leave it in sight. Unlike the nasty paws, these spherical molecules are not carcinogenic, apparently. They're big enough that they don't fit into the relevant spaces in the cell, and so they appear to be biologically benign, whereas the paws, some of them are quite nasty. They can act as nonlinear optical devices. If you shine light at one wavelength on certain doped fullerene molecule, you get light of another wavelength out, which is neat. It's been demonstrated by many people that they act as high-temperature superconductors. The record critical temperature for metal-doped fullerenes is about 45 degrees that I've seen. Certain rubidium atoms added to the surface of Buckminster fullerene molecules cause them to become superconductors at temperatures as high as 45 degrees. It's even been claimed, one paper recently, that fullerene derivatives act to inhibit the action of an enzyme which is necessary for replication of the AIDS virus. Implications are obvious. And also, these things are known to become ferromagnetic at low enough temperatures, and people have talked about the possibility of using them to make computer memory on a molecular scale. So the point I want to leave with you then is that I think this story of Buckminster fullerene is a marvelous example why it's important to do basic research. In this case, basic research in astronomy. There's no doubt in my mind that Buckminster fullerene would not be known today had not Proto come to Ottawa in the 1970s and worked with astronomers here to detect those big carbon changes. He would not have gone to Rice interested in trying to find out how they form and whether he could make bigger ones. So very often today, and I guess this is a political time in our country, but very often today, basic research is under assault. These are hard times. It's important to justify what one does in science. And I think this kind of story is just a wonderful example of how you cannot tell what fallout, what spin-offs will come from basic research. And I think that it's fair to say that this detection of C60 is the most exciting, potentially important scientific, at least chemical discovery of the century. So with that, I'll just put my summary overhead on. We've talked about molecular clouds. We've said they consist of gas and dust. Very rich chemical makeup for these things. The chemicals are important, not only from a chemistry point of view, although one can learn a great deal about fundamental chemical processes because of the unique conditions that exist in the clouds. But they're important, and I didn't mention this actually in my talk, I slipped over it. They're important because many of these compounds emit radiation, as we've seen, that can escape from the dark clouds. Consequently, they carry heat away from the clouds. Now, if a cloud wants to form a star, a part of that cloud has got to collapse, it's got to condense down. In so doing, that part of the collapsing cloud produces heat. It liberates heat from the gravitational potential energy. That heat raises the pressure of the cloud and prevents the collapse. If these chemicals did not exist and were not able to radiate that energy away in the form of the spectral lines I talked about, then star formation could not proceed. So there's a very important consequence that I should have mentioned in my main talk. The dust composition we're not certain of. It is certainly important as a blocker of starlight. It's the extinction of starlight. I didn't have time to talk about the icy mantles or coverings that form on the dust grains themselves. The unidentified infrared emission features, many people would say, but not all, are probably originating from these planar polycyclic aromatic hydrocarbon molecules containing perhaps 60 to several hundred carbons in each one. Diffuse interstellar bands, after 80 years, we still don't know what causes them. Stay tuned for that. Maybe in 10 years' time, you can have me back or someone else back, and he or she can tell you what's causing these things. And finally, the discovery of C60 has come by a not too indirect route out of fundamental research in astronomy. And I think that's an important thought I'd like to leave with you. Thank you.
I guess, Dr. Eddy, we will entertain questions now.
Yes, I'd be happy 2H, C3H, C4H, C5H, C6H. Care to say what sort of structures these things are? Yes. If I can find that quickly. Those are also linear carbon chains. They're very like the HCCCCN carbon chains that I talked about in connection with proto, except that they're missing, obviously from the formulas you cited, they're missing the terminating nitrogen atom, which makes them radicals, chemical radicals. Under terrestrial conditions, because they've got that sort of dangling bond there, as you know, they would tend to react. This is the overhead you're thinking of? We're talking about these things on here.
Some of these are polyacetylene as well.
That's right. That's right. If
But
you
they also lot numbers of carbons.
Yes. Yes. Obviously, if you add an H to the first one, you get just acetylene. An H to C4H, you get diacetylene. But the others, the odd number of carbons are also chains. They're all radicals, and if you make them in a terrestrial lab, they immediately attach something on to that sort of hanging carbon bond here.
For the molecular species that you can't synthesize in the lab, to what accuracy can the spectra be predicted by computation?
That's a good question. That's an important field of astronomy and spectroscopy, is trying to calculate what frequencies these chemicals produce, so you go out and look for them, either in the laboratory or in space. With the growth in computing power over the last couple of decades, the ab initio theoreticians have been getting better and better at this game. And I would say that typically today you could hope for about 1% accuracy in calculating the frequencies of many of these molecules, sort of from scratch. Actually, I don't think the theoreticians start quite from scratch, but what they do is they will do a calculation on a molecule and try to find another known molecule that has similar structure. And then they'll fine-tune their results. They'll scale their results for the unknown molecule on the basis of what they know for the known one. And by doing that, they can get, I think, within about 1%. That still is not sometimes good enough because, particularly at millimeter and centimeter wavelengths, the amount of frequency space we can cover with our equipment, either in the lab or in space, is quite narrow. Perhaps if we're working at a frequency of 100 gigahertz, in fact, if we're working at the JCMT in Hawaii at a frequency, let's say, of 350 gigahertz, our bandwidth we can cover at any one time is only 500 megahertz. I can't in my head just think what that is, but it's not. It's a pretty narrow slice in terms of the percentage of the primary observing frequency. And sometimes these lines are very weak, so even if you can calculate them to within 1%, it's still sometimes very difficult to go out and find the lines. And the other thing I should mention is, if you remember the slide of Orion, the overhead of Orion that I showed you, in many of these molecular clouds, you see spectral lines like that. And if you, let's say, as very often happens, you can identify all but, I'm seeing all but one or two. The density of unknown lines is sufficiently great that even though this one might happen to lie within 1% of the calculated frequency, you can't be sure that it's not coming from something altogether unrelated to what you're looking for.
How do they then, how can they be so sure that they have seen the molecules you had listed that they can't be synthesized in the lab?
Because, well, there are different ways. The best way is, if you just observe one line, as I indicated, you might agree, yes, that does match with the 1% of the observed frequency, but I can't be sure that it's not just a chance alignment. But once you've got one line measured with precision, and once you see it, you know exactly what the frequency is. There's no more any uncertainty in the frequency of that line. Then you know that for these molecules, other lines will be exactly harmonically related to that one. So if this, let's say this line was emitted, let's say emitted at 200 gigahertz, just pick a number, then for a typical case, you know that there will be another line at 100 gigahertz. If this is the right molecule, it will have another line at 100 gigahertz, another one at 300 gigahertz, and so on, multiples. So that you then have maybe 5 or 4 lines that you can measure, and the chance that all 4 or 5 are chance alignments from other compounds is very slim. And then double check, do the final check. You can go to the lab and you can say to your tame spectroscopist, look, we think we've got vanadium pentoxide here. Put the right chemicals into your discharge tube and see if you can match our measured frequencies. And so that by those kinds of checks and double checks, you can be virtually certain of what you're detecting. And the final thing you do is you can, if you think you've got vanadium pentoxide, you can snip off one of the O16 atoms and put in an isotopic variant of that, maybe O18, and you can calculate exactly what the relative shift in frequency produced by that mass difference is, and you should measure that. So you can keep doing these checks until you have really an airtight case.
I was just wondering, you were saying that there's probably going to be 100 molecules discovered in space by the end of the century. And I was just wondering, what are the really astrophysical implications of all these extra molecules you're finding? When you say you're using these things as tracers, but surely you've got lots now.
Yeah.
What are the new molecules really doing for you?
That's right. You made a very good point. With each, once you get to 95 molecules, getting to 96 is not really that significant. And it used to be 15 years ago that it really was sufficient to get time on an oversubscribed telescope by simply saying we want to go to look for molecule X because we think we have the frequencies measured in the laboratory and it should exist in space. And right, telescopes oversubscribed by a factor 2 or 3 times, but it's important enough work to go and do it. Nowadays, you just about can't get time with that kind of. The next new interstellar molecule, but just for the sake of getting it, is not justifiable, generally speaking. There are still some of the lighter molecules which should exist in space in sufficient abundance to have strong lines and be important, and which might exist in special astrophysical circumstances. For example, there's a whole class of chemistry that is enhanced by the presence of shock waves. And the shocks are fairly common in space because there are all sorts of situations in which you can have material moving faster than the speed of sound. Shock waves produce heat, and they can drive chemical reactions which normally would not happen in the cold interstellar clouds. Also, shock waves can drive grains together so they collide and shatter, and they can liberate from the grain surfaces molecules that have condensed out onto the grain, so you can get whole new reactants. So shock chemistry is a whole different kind of sort of new chemistry, and there it's sufficient still to say, look, here's a molecule which the chemists tell us should be produced under shock conditions. We want to go and look for that because it could be a sign, wherever we see it, of the presence of shock waves associated with a star, a wind from a star, or colliding supernova remnants or whatever. So you're right. Just getting the 96 molecule isn't important unless it has an astrophysical, special astrophysical significance. The one exception to that might be glycine. People have been looking for glycine in space for a long time. It would be it is the lightest known amino acid, has obvious press potential as a biological molecule, and people are still looking for glycine for the sake of finding glycine. I was talking to a chemist at Illinois just a week or so ago, who says he has one line, come back to this gentleman's questions here, he has one line at the right place to match one of the glycine lines. Glycine has a spectrum measured in the lab, so he knows where he can look. But he can't be sure that it's glycine. It could be some other chance alignment. He's got to go back to the telescope and look for other lines. But that would be interesting, just sort of from a biological point of view.
Yeah, are you limited to looking at the clouds within our galaxy, or can you also measure that which is beyond our galaxy?
No, we're not limited to our galaxy. We can see many of these stronger emitting molecules in other galaxies.
Is there any difference, or do they appear similar in terms of composition?
They do appear similar insofar as we can tell. I wouldn't say there are any obvious differences. Certain chemicals we think now, just now begin to think, in fact there was a paper appeared just in the last month or so suggesting that certain kinds of chemicals will be enhanced in regions where there are strong cosmic ray fluxes. This is, well, I won't go into why, but and strong cosmic ray fluxes are likely to occur where there is a lot of hot, massive young stars forming, because these hot, massive stars are the ones which evolve most quickly and become supernovae. And supernovae produce cosmic rays. So almost as soon as a 30 or 40 or 50 solar mass star is formed, it flows up. And there are these so-called starburst galaxies, where there are a lot of massive stars recently formed, a lot of supernova activity, and hence a lot of cosmic ray fluxes. And so the prediction has been made that you should see enhancements in the abundances of molecules like HCN, because the cosmic rays can affect the chemistry. Just a final note on your question, the most distant galaxy in which a molecule line has been detected is quite a hot topic now in astronomy. It's called RASC 214. This is a galaxy whose nature is not completely agreed upon, but it exists at an extreme redshift. The Z, which is a measure of the Doppler shift over the speed of light, is about, I think it's about 2.1 or so, which means that this galaxy is really cosmologically distant from us. And the interest in these distant galaxies, of course, is the search for proto-galaxies, which so far has been unsuccessful. But at some epoch in the past, sometime in the past, galaxies had to form. We see them today. We don't know really what a forming proto-galaxy should look like. So a lot of people are interested in finding them.
I wonder if I could ask a question. We know that molecules are made of atoms, and that atoms were the first three elements, hydrogen, helium, a little bit of lithium, were created in the Big Bang. The other atoms, the other elements, are primarily created in the process of the stars shining. So the thing is that as the galaxy evolves and more stars, new generations of the stars, the population one type of stars increases, we are going to get a different admix of these chemicals as compared to what it was 10 billion years ago or whatever. So can we not sort of see a historical thing we could, by judging these admixes of the various chemicals that are present, be able to sort of trace historically development of this galaxy or that galaxy and sort of follow through as they develop?
Yes, I think in principle that should be possible. It hasn't been done yet because it's very difficult to see these molecular lines far enough in galaxies that are far enough back in time. This RASC 214 galaxy I was referring to, the CO lines that have been seen are very, very weak. And it's just difficult to get enough statistics, I think, yet to look at that question. It's certainly is true that, and this is maybe one of the problems in looking for protogalaxies in these molecular lines. Presumably when the first galaxies or protogalaxies condensed out of whatever medium they condensed out of the Big Bang remnants, by definition, in the very first blush of a galaxy's existence, there are no stars, presumably. The galaxies condense as gas. If there are no stars, then there can be no heavy elements, because as you said, it's within the stars that the heavy elements are synthesized and then seeded into the galaxy by supernova explosions. So if there are no heavy elements, there can be no, in the very initial stages of the galaxy's existence, there can be no CO, there can be no HCN, there can be no molecules to look for. So it may be that protogalaxies will have to be detected through, for example, 21 centimeter radiation from atomic hydrogen, which would have been around during protogalaxy stage. But there really aren't enough statistics to address the kind of question you're talking about. But in principle, you could do that.
Any more questions?
Sorry, just a very quick one. You mentioned that extinction occurs within our galaxy. Is there any small amount of extinction that occurs between galaxies? I realize it could be very small, but has there been anything measured between galaxies?
Not so far as I know. This is a question which I believe has come up from time to time, the question of what might exist between the galaxies. And well, so far as I know, and I'm pretty sure this is true, there's no evidence for any kind of extinction between the galaxies. There certainly is extinction within other galaxies. Other galaxies, as I've indicated, show the same kind of chemistry as we see in our own Milky Way.
Any further? Sir?
Is there anything really known about the chemistry of the clouds within our own galaxy? In other words, has anyone got a real idea of the composition of these clouds? It's very exotic looking molecules. Right? Is this a steady state or is this an equilibrium situation? Or is it just too early?
I think with 95 or so molecules known, we certainly have identified the major players in terms of the composition in any cloud that we want to look at. However, it is not true that all of the clouds we look at are in a steady state. Clouds we know are formed and go through their lives and are broken up by various processes. For example, when stars form inside molecular clouds, as we've seen they do, they can act to disrupt those clouds by means of the radiation pressure and by means of very high velocity winds. When stars explode to become supernovae, they can send a shock wave blasting off into space which can collide with the cloud, disrupt it, change the chemistry in it, as I was talking earlier. So while there are clouds which certainly appear to be very quiescent and which one might say have reached equilibrium, there are problems even with those, because one of the things we see when we look with our radio telescopes deep inside these dense clouds, we see two things. We see carbon atoms, free carbon atoms, which all of the chemical models predict shouldn't exist. They predict that the carbon should have combined to form molecules in these dense clouds. That's not happening. Something has been suggested is acting to stir them up, to disrupt the internal composition of these clouds so that the carbon atoms are still around. The other thing that's been noted is that every time a molecule strikes a grain inside these dark clouds, almost every time, it should stick to it. And on that basis, you'd think that a cloud that's been around for 10 million years or so should have all of its gas molecules frozen out on the surfaces of the grains. Yet we still see lots of evidence of spectral lines with free gas molecules. We don't really understand why that's the case. In other words, there's evidence that something is keeping these clouds constantly stirred up.
Any more questions? Rick, would you thank the speaker?
I know many of us have been out on a dark night looking up at the Milky Way and observed the many dark clouds that make the southern Milky Way so interesting. It's very interesting to be able to see now what's some of the chemistry that's going on inside those clouds, and how important it is to chemistry, to life on Earth, and to the science of astronomy. I think Dr. Avery's given us a very interesting presentation this evening on the subject, given us a lot of background. I know I'll be able to go and look through Nature and Science now with a better idea of what they're talking about. I'd like to thank Dr. Avery for coming out this evening, both for myself and on behalf of the people here. Thank you.
Well, this just about concludes the meeting. I just want to draw your attention to the two announcements that are very nicely hidden by the screen, namely that on the 9th of November, we're having our annual dinner meeting at Algonquin College, and that after the meeting, I'll have the RASC calendars for sale. Meeting's closed.